We are looking at 912. How does it change? Last week we looked at a lot of rates of change from data, and today we're going to do some similar stuff. So today's lesson we're going to look at data and extend our understanding to the graphs of data as well. We will look at how the average rate of change can be seen from both data and a graph. So we've got this table below showing the population for Australia in the given years. In 1970 there was 12.51 million people, and all the way up to 2007 there were 20,074,740,000 people. So we want to enter the data above into our calculator by creating a plot of the data and finding an equation to model. So we're going to press some buttons on our TI. I'm going to press Stat, and then we're going to press Edit. And then we should have an L1 here and an L2 here. And you can delete those out if you'd like, or you can just write over them. When we are using years in a table, it is usually pretty convenient to use years since as one of our values instead of the actual year. If we use our years, 1970, 1973, those are pretty big numbers to use. So if we use years since 1970 as our L1, 1970 would be year 0. And in year 0, there was 12.51, again, million people. So the 1973 would be a 3, and then 13.27. Now these numbers should all be going into our calculator. So I'll give you a moment to keep pressing those buttons. Once we get that data in, it should have 15 pieces of data, 15 years followed by 15 population estimates. Make sure that those match. If you have 16 in one and 14 in another, we'll get an error later. So get those in. Now we want to create a plot of the data on our calculator. So press second, stat plot. Should be right above the y equals. And we want plot 1. Press enter and turn it on. And you can change the type. I think it's usually the default is the scatter plot. And now we want to change our window. For years started in year 0 and went to year 37, we should change our window for x's to be 0 to 40-ish. And then our y's went from, let's go from 0 to maybe 25. That would probably get us a pretty good window for seeing our scatter plot. And then remember, if you had anything else in your y equals, it'll also try to graph it. So clearing out whatever was in y equals would be a good idea. You should get a pretty solid scatter plot. If you did that window, this is again a rough sketch, but find an equation to model this data. I would say this is some linear data. And so we can press another button, press stat again, but instead of going to edit, go over to calculate. And let's go to line of regression number 4. And it should automatically take line 1 and line 2. And we should get A equals 0.223 and B equals 12.36. So that we can write y equals 0.223x plus 12.36. Now go put that into your y equals, and let's take a look. And for me, that graphed a line going straight, nice, through there. So let's answer some questions. B says, if the population growth of Australia continues in this pattern, what will they expect in 2020? Well, 2020 would be 50 years after. So if I just put in 50 for x, so I can calculate the value at 50, we should figure out that 50 years later, 2020, they should estimate a population of 23.51 million. And then in C, we start getting into our f of b minus f of a. From the table, what was the average rate of growth? Delta p over delta t between 1970 and 1999. So we want to write 1999 was 18.94 million minus 1970 was 12.51 million over, we could do 1999 minus 1970, and that should get us a number very similar to our slope, 0.221. But what does that actually mean? That represents an average rate of growth of 221,000 and let's say 700 people. So understanding what this slope meant, what this rate means, is also important, of course. And it says, using our model, what will the average rate of growth be between 99 and 2020? So doing 23.9 million minus the 1999 was 18.94 over 2020 minus 1999. I believe we should get somewhere around that 220,000 people mark. Showing this delta p over delta t work is very important in this chapter. When is the growth increasing most rapidly? Looking at that table, I'd like you to study it a little bit and see if you can find between what years do you think it is growing the most. And we could even look at our graph as well. Look for which point kind of stands to stick out a little more than the rest. And then I'll do one more with you. Let's do number 918. Banks advertise rates in both actual rate and annual percentage rate. APR is a word that you'll see if you go to the bank and get some information on putting some money in, which is probably a good idea. Suppose you deposit $1,000 into a bank that offers 6% annual interest compounded monthly. So that's our 1 plus 0.06 divided by 12 to the 12 times t. And in this case, how much money would you have after 1 year? So we'll leave the 1 right there. We would have $1,061.68. So what percent did we earn if that was compounded in the APR? So how APR is calculated is, what would it have been if we calculated it 1 time per year? So I think a long time ago, you'd have been able to look at this and said, well, that's not just 6%. You would say that that is 6.168%. Not dollars, percent. And we could do that by just dividing this number by 1,000, and that would get us 1.06168%. But we know that the 1 is part of the initial, so the 6.16% would be our annual percentage rate. And then very similar problem, what would the APR be if the bank offered continuous compounding? So that is our 1,000 e to the RT equation. So that should get me $1,061.83, which is just slightly more than compounded monthly. But it asks for the APR, so our APR should be this divided by 1,000 again. So 6.183, let's call it. And then again, let's call it percent and not dollars. Good.